So in this video, we're going to look at radical functions, and we're actually going to specifically look at square root functions. We'll look at other roots in class together. So let's start with the most basic radical function, y equals the square root of x. Now, like with rational functions, we are going to get domain restrictions, but in rational functions, that restriction arose because we can't divide by 0. In radical functions, it's going to occur because we want everything to stay in the realm of positive numbers. So what that means is that this x value, the radicand, has to be greater than or equal to 0. So that gives me, using proper notation, this domain. Other than the fact that it has to be greater than or equal to 0, it's going to be any real number. For the range, we're going to make use of the fact that this is the principal square root. So we know that when we take a square root, we usually do positive or negative. So if there is no positive or negative written, then what is being expressed is the positive square root. So that means that the range has to be greater than or equal to 0 as well, because the square root is going to be the positive root. If I did want the negative root, I would have to say so. I would have to actually write y equals the negative root of x, and then that would have the negative range. So it would end up being, if I had y equals negative root x, the domain would be the same, but the range would be y is less than or equal to 0 and any real number. So let's try and think about what a sketch of this would look like. Because y and x both have to be greater than or equal to 0, I have a starting point at 0, 0. Now, if I just think of a few values, then I'm going to use x values that are perfect squares just to help sketch this. So the square root of 1 is 1, so we have the point 1, 1. The square root of 4 is 2, so we have the point 4, 2. The square root of 9, 7, 8, 9, is 3, so we have a point here. And what's happening is we get a curve that is extending out that way infinitely. This actually is half of a parabola. So if I were to graph y equals negative root of x, so the square root of 1 would be the negative 1. The square root of 4 would be negative 4. So we're looking at the negative root for each of these. So I would get this other half of the parabola. If they were both put together, it wouldn't be a function. I would have the relation y squared equals x. That would be both of them together. But because I'm looking only at functions here, I'm just looking at one branch or the other. So the top branch here represents y equals the square root of x. It does have some of the, if I had the whole parabola, it would have an idea of symmetry like we have with quadratic functions. But because we're only dealing with half of it, it doesn't have that symmetry. We do often still think of this as being the vertex, the domain endpoint. All right, so now that we have that basic idea, let's look at something a little more complicated. And some of the concepts that we learned with quadratics, as far as transformations, will be applicable here as well. So if I think of this next one in terms of what I know about quadratics, I will have a vertex at the x value that makes the radicand, the thing that's inside the function, equal to 0. So x minus 5 will be equal to 0 when x equals 5. So I'm going to have a vertex where the x value is 5. I also use that radicand to determine my domain, because x minus 5 has to be greater than or equal to 0. That means x is greater than or equal to 5. So proper notation, here is my domain. You are, of course, welcome to use interval notation as well. Now for the y value of the vertex, what we learned from quadratics would seem to suggest that it's going to be 3. And in fact, if I reason out what would happen, that's going to be true as well. So because I know that x minus 5, the root of x minus 5, I want negative 2 times that root. So because x minus 5 would be positive, if I multiply it by negative 2, that is going to have to be less than or equal to 0. And then once I add 3 onto both sides of this inequality, that means it's going to be less than or equal to 3, which means y is less than or equal to 3. So what we suspected from quadratics, that the vertex start point for y would be 3, is true. And also what you might have suspected from quadratics, that this would open downwards because we have a negative 2, is also true. Y is less than or equal to 3 instead of greater than or equal to 3 in this case. So to sketch this, I have the vertex at 5, 3, so right there. I know that the y value has to be the x value has to be greater than 5, so I need to head towards the right. But the y value has to be less than 3, so we also need to go downward, which means that the curve is going to end up looking something like this. It's the bottom branch of the parabola, but it does still head off towards the right. Finding that specific x-intercept is something we'll come to later, so I'm not going to worry about that too much, although if you'd like to play around with it, you certainly can. There's no y-intercept in this case because x can't be 0. It has to be greater than 5, greater than or equal to. All right, one more example of this, same basic idea. I'm going to consider my domain first. So the radicand, 3 minus x, has to be greater than or equal to 0, which means 3 is greater than or equal to x, or put another way, x is less than or equal to 3. This does tell me that for the vertex, the x value is going to be 3. So the value that puts a 0 inside of that function. The y value is going to be -4 just from looking at the equation, but let's actually play out that reasoning. I know that 3 minus x has to be greater than or equal to 0 because that's a principal square root. If I multiply it by 1/3, that doesn't change the sign at all, so it's still greater than or equal to 0. And then if I subtract 4, I'm going to get something that is greater than or equal to -4. So y has to be greater than or equal to -4. So again, proper notation, let's state our range. Y is an element of the reals. All right, so there's the range. And I can now sketch this graph, knowing that my vertex, oops, I don't know why I wrote a 0 here when that should clearly be a 3. The vertex is at 3, -4. And I know, because the domain and range being what they are, x has to be less than 3, so we have to go to the left, but y is going to be greater than -4, so it has to go up. So that is going to be a function that moves in that direction. Now, in this case, I could actually figure out my y-intercept. It's not a nice rational number here. The y-intercept is going to be root 3 over 3 minus 4, so it's not super helpful in terms of just making a rough sketch of the graph. But what I can see here is instead of having a vertical reflection, I've had a horizontal reflection. That wasn't something we ever considered with quadratic functions because they were symmetrical in the horizontal axis, in the vertical axis. So a horizontal reflection wouldn't have changed anything. But for these radical functions, we do need to consider not just vertical reflections, but also horizontal.